This module is part of the Satellite Foundational course for JPSS and focuses on oxygen and water vapor absorption bands. The learning objectives are 1. To identify the location of the oxygen and water vapor absorption regions in the microwave spectrum, and 2. To describe how varying levels of absorption and transmittance across the oxygen and water vapor absorption regions affect brightness temperature and can be used in determining temperature and moisture profiles. Microwave temperature and moisture profiles are used operationally with NuCap soundings and total and layered precipitable water products, and indirectly used with incorporation into numerical weather prediction models. More information will be presented on NuCaps and NWP in later modules. Absorption and transmittance of radiation in the atmosphere is dependent on gas molecules that selectively absorb across broadband or very narrow frequencies. This figure shows zenith microwave transmittance of a cloud-free atmosphere for 4 different global regions based on moisture. Note this is slightly different from the graph in the previous module, as frequency along the x-axis is not on a logarithmic scale. Transmittance is shown on the y-axis. From a satellite perspective, a transmittance of 1 represents a transparent atmosphere so that the surface is sensed, while a transmittance of 0 represents the center of a major absorption region and a level higher in the atmosphere is sensed. Oxygen is a well-mixed constituent in the atmosphere, while water vapor is not. Based on the transmittance spectra for dry, polar, mid-latitude, and tropical regions, which 2 of the 4 spectral regions labeled A, B, C, and D correspond to oxygen absorption? We encourage you to pause the video and think about this. Is it what you expected? Regardless of the amount of moisture in the atmosphere, the strong absorption regions where transmittance goes to 0 for all spectra are near 60 GHz and 118 GHz. These correspond to oxygen absorption and indicate a well-mixed constituent. What does that mean for water vapor absorption? For the dry atmosphere, the transmittance is very close to 1. In this scenario, the lack of moisture means 2 absorption regions aren't found, the water vapor absorption regions at 22 and 183 GHz. Water vapor is not well mixed in the atmosphere, but variable. Even outside of absorption regions, this affects how clean or dirty a window region can be. The drier the atmosphere, the more transparent. The moister the atmosphere, the less transparent. Let's first focus on oxygen absorption. A strong absorption band due to molecular oxygen is centered at 60 GHz. This band plays an important role in satellite retrievals of atmospheric temperature profiles. A second, narrower oxygen band is also present at 118 GHz. Strong absorption results in an opaque atmosphere at the centers of both bands. An atmospheric temperature profile is obtained when measurements are captured for a series of closely spaced narrow frequency ranges on the edge of a strong oxygen absorption band, in this case, near 60 GHz. The concept of the weighting function will help us to understand how this works. At a given frequency, the weighting function for radiation represents the contributions from different heights in the atmosphere. The closer the measured frequency is to the maximum absorption for a well-mixed constituent, the higher in the atmosphere the weighting function will peak. Weighting functions from the Advanced Technology Microwave Sounder, which will be described in a later module, for channels 1 through 15 are shown for a standard mid-latitude atmosphere. Channels 1 and 2 fall in a window region that senses near the surface. Channels 3 through 15 are located along the oxygen absorption region centered at 60 GHz and are used in measuring temperature over a range of heights in the troposphere and stratosphere. Channel 3 at 50 GHz is farthest on the edge of the absorption region where it is sensing closer to the surface. The remaining channels have frequencies approaching the center where oxygen absorption is strongest and the atmosphere is opaque. Channels 10 through 15 are narrow and overlapping bands. The varying bandwidth is indicated with a plus-minus symbol. For more information, refer to the paper listed. The vertical resolution of the retrieved temperature profiles is dependent on the number, peak distribution, and sharpness of the weighting functions. Can you determine which channel presents the maximum absorption for oxygen? Hint: the weighting function for maximum absorption for well-mixed oxygen peaks highest in the atmosphere. This is a loop of ATMS brightness temperature imagery for channels 3 through 15. Notice how brightness temperature changes with frequency from the edge of the oxygen absorption region towards the center. You're encouraged to use the link provided to replay and pause the loop at your own pace. Think about when surface features are apparent and when they disappear, as well as how a temperature profile at the poles would compare to the tropics. Current and archived imagery can be found using the provided link. Let's take a simplified look at how this information is processed. Microwave radiance is sensed by the satellite and transmitted back to Earth. The microwave integrated retrieval system is initialized for the radiance values to be incorporated. The outcome is temperature interpolated to pressure levels, which we will see in the next animation. This is a loop showing mirrors temperature retrievals from the same time as the brightness temperature loop on a previous slide, but now displayed on pressure levels from 950 to 100 millibars, used in vertical temperature profiles. This type of information is also assimilated into numerical weather prediction models. Links are provided for the animation and archived imagery. We'll now take a look at water vapor absorption. There's a very strong water vapor absorption region centered at 183 gigahertz. This band is used in microwave retrievals of atmospheric moisture profiles and provides data to create microwave water vapor products. There's also a weak water vapor absorption region at 22 gigahertz. The weighting functions for ATMS channels 16 through 22 are shown. Channels 17 through 22 are located along the water vapor absorption region centered at 183 gigahertz and are used in measuring atmospheric moisture over a range of heights. Channel 17 at 165 gigahertz is farthest on the edge of the absorption region where it is sensing closer to the surface. The remaining channels have frequencies approaching the center where water vapor absorption is strongest and the atmosphere is opaque. The varying bandwidth is again indicated with a plus-minus symbol. Water vapor is not well mixed, so the weighting function peaks are highly variable. The height of the peak is lower in a dry atmosphere and higher in a humid atmosphere and/or where clouds are present. In a standard mid-latitude atmosphere, as with the weighting function shown here, the water vapor is concentrated below 15 kilometers. This is a loop of ATMS brightness temperature imagery for channels 17 through 22 with the same color bar throughout. Notice how brightness temperature and the transparency of the atmosphere changes with frequency from the edge of the water vapor absorption region towards the center. You are again encouraged to use the link provided to view the loop at your own pace. Think about when surface features are apparent and when they disappear. Current and archived imagery can be found using the provided link. A following module on the influence of clouds and precipitation will provide an overview of how microwave remote sensing is used for moisture products and in determining precipitation type. The upcoming animation is processed information. In this case, the microwave radiances sensed by the satellite are processed with mirrors to get water vapor content interpolated to pressure levels. This is a loop showing mirrors water vapor retrievals from the same time as the brightness temperature loop on a previous slide, but now displayed on pressure levels from 950 to 100 millibars, used in vertical moisture profiles. Note that the color bar changes a bit throughout the animation. For instance, there isn't a sudden jump in moisture from 700 to 600 millibars. This type of information is assimilated into numerical weather prediction models. To summarize, the microwave spectrum is influenced by strong absorption regions due to oxygen, which is well mixed in the atmosphere, and water vapor, which is variable. Channel selection on microwave sounders takes advantage of these absorption regions and the weighting functions of different frequencies for driving vertical profiles. Oxygen absorption is used for temperature profiles, and water vapor absorption is used for moisture profiles. Applications in precipitation estimation and cloud retrievals will be discussed in a later module. For more information, please visit the following resources. I'll leave you with a snippet from the textbook by Grant Petty, which highlights the importance of microwave remote sensing and the data it provides. These retrievals provide indispensable information about the current state of the atmosphere to numerical weather prediction models. Without the availability of satellite-derived temperature structure data, accurate medium and long-range forecasts, 3 days and beyond, would be impossible almost everywhere, and even shorter range forecasts would be of questionable value over oceans and other data-sparse regions.